Yeah, hi Aditya. Let's wait for another minute or two for others to join in. Yeah, hi guys. All those who are there, if it would be really nice if you can just put in your name. Yeah, so hi everyone. Let's begin. I guess I can see a few of them, few of you already joined in, and I assume that the rest would be just joining up. Yeah, so hi everyone. Yeah, so this is today we look at energy change in chemical reactions, basically the chapter which deals with thermodynamics and thermochemistry as such. Now, everything to do with heat, energy, work, and one of the most important chapters for your upcoming board exam. I'll also try and touch base upon a couple of problems, maybe a problem or two, to really show how we can approach them at the same time. How can the answer be presented? I can see that Aditya is already in, and a few more. I can see. So let's begin in understanding how this chapter really unfolds. If you have any questions in between, you can always put the questions up, on the chat, and I'll be happy to really address them. Now, the this chapter specifically deals with what really means by having an energy change in a chemical reaction, and how does it affect the other enthalpies or energies as such of the reactants and products. Now, so let's go step by step. Firstly, let's understand how chemistry and energy is related primarily. So, if you really see that the energy as well as chemistry is related in terms of the work or transfer of heat. Energy means that you have some ability to do the work or some ability to change this energy into some other energy form of energy. And one of these forms is heat. And heat is this form where uh, if there is a temperature difference between two objects, then the energy is exchanged. So heat is that form of energy that flows between two objects because of their difference in temperature. So temperature is like the potential difference that we see in electricity. So when electrical energy has to flow, there has to be a potential difference, and when heat has to flow, there has to be a temperature difference. So heat is just one form of energy as we are seeing this. And what are the other forms of energy? Some energy are explicitly visible as light. Some of them is electrical, as we just mentioned a few minutes ago. A few of them can also be visible as mechanical energy, where we talk about kinetic and potential energy. So whenever there is an energy exchange, whether it is from a chemical energy or into a chemical energy, the forms of energy that we can really see is in either light, electrical, or mechanical forms. Now, let's look at a few examples. So, if you see, let's when we burn peanuts, with sufficient energy, either in a cup of water or or also when peanuts are burnt, the energy that comes out of it, that actually heats up the water in a pan. It means that there was some energy inside peanuts that actually turned or converted into energy which was supplied to water. And once it was supplied to water, its temperature really increased. So burning peanuts is one example. The second example is this is a jelly made up of sugar. And when you put this sugar in KClO3, which is a very strong oxidizing agent, you'll find that the sugar entirely burns. It turns to char. So that's also another form of energy where I'm actually not using any heat or any thermal energy. At the same time, converting sugar into carbon, or for that matter, char. So this is another form of energy that can be extracted out of compounds or molecules and converted into some different forms. In the earlier form, light as well as heat was found. In the second form, it is simply heat energy that was produced from chemical energy. Now, so we understand that energy is intricately related with the way that the substance exists, or there is some energy that is there inside a substance in its molecules or in its atoms. Now, if that is the scenario, how do we really study this chemistry and its energy changes? And for this particular purpose, we need what we call as a thermodynamic system. Like we have free body diagrams in mechanics, like we have circuits in electricity, or in sound energy also we have systems where there is an observer and there is a sound emitter. The very same way in thermodynamics, we have something called as a thermodynamic system, where a system is that quantity of matter or region which is what we want to study. So anything that we want to study, observe, decide upon, that is put inside a certain constriction of space, constriction, or what we can say an envelope of space, and that is what we call as systems. Now, anything that is outside the system is surrounding. So from the surrounding, either the observer could be anywhere. He could be inside the system, he could be outside the system, that is in the surrounding. And the surrounding and system can play with each other, giving energy or taking energy. But all of that put together, surrounding and system put together, we get the universe. And how do we really strictly, if we have to separate the system out of the surroundings, we'll have to separate it out of an imaginary boundary. Now, please note, this boundary actually looks two-dimensional, but it's not a two-dimensional boundary. It's actually a something like a three-dimensional boundary. It's a complete packet, like a vessel or like a sphere. So it's a three-dimensional boundary, and this three-dimensional boundary can be defined as either a real or imaginary layer that separates the system from its surroundings. It is through this boundary that the system and surroundings exchange energy, mass, or any of the other quantities that they want to do. So these are boundary, system, and surroundings. And I also told you an additional definition of universe. System plus surrounding basically means universe. Now, if you really look at systems, these systems basically are of three types. They are called as closed systems, open systems, and isolated systems. And we'll look at one of each of these one by one. Yeah. So I think Ronak has joined. Hi, Ronak. Yeah, so the first system is closed systems. So now in closed systems, you'll see that the masses are fixed. Closed systems, you are allowed to only exchange the energy, but not the mass. So you see, the mass exchange is not allowed, but the exchange of energy is possible. This is possible only if the boundary is capable of exchanging energy, and so therefore it should be a conductor. Okay, a conductor. When we say conductor, we are talking about thermal conduction, not electrical. So this is very important. So when the boundary is a thermally conducting boundary, or in some cases we have also seen that the boundary is invisible, there is an imaginary boundary, in which case, of course, there will be conduction possible. In such scenarios, we end up getting closed systems. So closed systems, you will find that the mass is not exchanged, and therefore the mass is always constant. In closed systems, the mass is always constant. Now, and energy keeps on varying. So this is closed systems, and it's also called as fixed masses system. That is the first type of system. Now, please note this: closed systems does not necessarily mean that it cannot conduct energy completely. Not in pure form of energy, but there is a moving boundary that can be possible, and we know that whenever a boundary moves, work can happen. So this is a very interesting case that I wanted to show in here. Is that as boundaries move, even a closed system is able to give work out or take work in. The only problem is you cannot directly give out or take in heat. Heat is not allowed, or any form of other energy is not allowed, but work can definitely be done. So this is a closed system with a moving boundary, and which actually helps us exchange work as such. And work is a form of energy, therefore energy exchange only through work is possible, but not otherwise. Okay, so that's a closed system. And then we have open systems. In open systems, you'll see that both energy and mass, they can be exchanged. So you actually have an open end, and you have a end which can take in or take out mass, and of course energy can be exchanged, and therefore it is a conducting medium, as we had said in the previous slide as well. Now you'll see the volume of this can actually be maintained pretty much, because the volume is constant. You can also find this as that a control volume, which means that like a constant volume that you can come in. Now there is another point to the system. As the mass comes in and gets out, how is the volume constant? We are saying volume of the vessel or volume of the system is constant, not volume of the gas. Okay, so substances can come in, substances can go out, and mass can be exchanged, energy can be exchanged. This is what we call as open systems. Good. Now, after this, let's look at isolated systems. Now, isolated systems are those where neither energy nor mass can be exchanged. Now, there is a very interesting diagram that I wanted to put in here. Most of the times, we think that system and surrounding are only one, but you can have different surroundings and one system. Let me give you an example. Let's say you have a cup of tea. This cup of tea is put inside a thermal insulated thermos, and like a bag, like a non-conducting bag, an isolated bag. And this cup of tea is you can say closed. At the same time, maybe you have some another food material like sandwiches and maybe some vegetables. Now you'll see that if we are wanting to study only the energy changes in the cup of the tea, it still exchanges energy between the sandwiches or the vegetables. The only thing is that it will not go out of the packet, out of the thermal insulation that we have put in. So a system can exchange energy between the surroundings, but whatever boundary we have drawn, and if we say that this boundary is an isolated system boundary, then it cannot go outside this boundary. Internally, there can be any exchanges that are possible, they can do that. So an isolated system boundary is that boundary where energy or mass both cannot be exchanged. So generally we call this as the main system or several systems. and then there are surroundings which are considered as an isolated system. So this is basically a main system, and then the surroundings etc are called as associated systems, and the boundary is differentiating it from all other types of systems. Now, so it means that energy can be exchanged. Now, what are these types of really where do this energy really stay in a system? What are the types of energies that the system can hold? So for this, we have to understand a few more concepts, and the first concept is potential energy. Now that anyone who has climbed up a mountain, or there's just a pic that I've mentioned where these guys have really climbed atop a bridge, and there is another person who is wanting to climb a diving pad on a swimming pool. So when he climbs atop this swimming pool, the diving pad, he actually earns some potential energy. So potential energy is energy of a motionless body. Please note, it is not energy of something that is moving, but it is the energy of something that is not in motion, but only by virtue of its position. So depending on where in gravity it is, whether it is at the top of the driving pad, or it is on a bridge or something of that sort, you'll find that the potential energy can be assessed. So this is first form of energy, but this is for very large objects. How really potential energy is exhibited at molecular level? Now at an atomic scale or molecular level, we'll find that the sodium and potassium, so there is an NaCl structure that I've shown here. This is a structure of salt. So you'll find that Na plus and Cl minus are the cation and anions in a salt structure, and both of them attract each other, and therefore there is some potential energy between them. These two atoms can bond with each other, and as they attract with each other, if the atom is moving far away from, let's say Na plus is moving far away from chlorine, then you will find that the attraction will reduce. If it is closer, then there is a very strong attraction. So because of this attraction, very similar to the gravitational attraction, the particles have higher or lower potential energy. So these potential energies can affect because of this. I've just shown a quick small two particles here, and you will find that the Na and the chlorine can attract each other, and this is how their potential energies vary. So on an atomic scale also, this potential energy is very much existent. The same, when we this potential energy can be converted into kinetic energy at a very macromolecular level, or for example at a human level. When we actually jump out of the diving pad, we find that we can actually gain the potential energy, the kinetic energy, which is converted from the potential energy, and you can dive inside the in the swimming pool or the river, wherever we are diving. So potential energy gets converted to kinetic energy in the very same fashion. Between the atoms here, sodium and chlorine, the potential energies between themselves gets converted into kinetic energy as the atoms start going further apart. So kinetic energy is energy because of its motion and not because of its position. So that's another form of energy that's existing inside the molecules. Now this kinetic energy can be in multiple ways. One is that it can be because of rotation. So this is a water molecule. For example, this red one is an oxygen, and the white ones are your hydrogens. Yeah. So hi Aditi. Aditi is joined in, I guess. Yeah. So because of rotation and because of vibration, there is kinetic energy, and also because of translation. Translation means only going straight forward. Vibration means the hydrogen and oxygen are vibrating between themselves. Please note, the vibration is between hydrogen and oxygen. So this is the way that the molecules vibrate between themselves. This is how it will vibrate. This one will keep on vibrating this way. So these vibration energies, and then you also have the rotational energy, where you can, the molecule completely spins. So there is a kinetic energy because of that, and then the molecule is going straight. There is a kinetic energy because of translation. So these three plus potential plus your kinetic energy is 5, and then the interactions between the electron and the nucleus. So those interactions all put together. So yeah, I'm sorry. Yeah. So all these energies put together, you end up getting a summation of total energies that basically a particle has, and that is what we call as internal energy. So we just understood what is a system, and what is a surrounding. We understood what is a boundary for people who have just joined in. Hi Neha, Aditi. So we have seen systems, types of systems, surrounding, boundaries, and then we are talking about different types of energy that these molecules basically possess. And in that we saw there are 7 types of energies: translational, rotational, vibrational, potential energy, electron energy, electron neutron energy, nucleus energy, and nucleus interactions, as you can see in these two figures. And so all of these put together, the energy together is called as internal energy, because all of them individually cannot be ascertained, but all they together can definitely be ascertained, or their value can be established. So because of this establishment of the value, we call them together as internal energy. Now now uh, so so the internal energy is represented generally by E or U, and this internal energy of the system basically depends on not only the number of particles, of course, because the number of particles will increase the mass, and we know that kinetic energy is half mv square, so definitely number of particles actually change the internal energy. Kirtana has also joined in. Hi, Kirtana. And it also depends on the type of particles. What do you mean by type? Is basically, are the particles diatomic, are the particles triatomic or polyatomic? Why? Because the vibrational energy is different for different particles. So this internal energy also depends on type of particles. At the same time, it depends on temperature. So let's say I've just shown you an example here. So there is a lot of energy inside this small bomb, the one that the cracker that you use during our festivals. And let's say if you are wondering how much of energy does this cracker really have, and this cracker actually their energy also depends on temperature. Let's try and increase this temperature. So basically, when we light the cracker, we are trying to increase this temperature. So in the solid, that the all the particles were sitting pretty uh, 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 arranged pretty regular in a regular fashion. Suddenly, when it goes to the gaseous form, all the particles are let loose. So the potential energy and the kinetic energy are changed when you go from solid to gaseous, and that's exactly what happens when the cracker bursts. So all the internal energy that was there inside the cracker is now into the gaseous form, and its energy actually has increased because of the rise in temperature. So the higher the temperature, the higher the internal energy, and so the change in temperature can directly be ascertained to the change in internal energy. So at any point of time, let's say if you have to know what is the change in the internal energy, some like we write it as delta U or delta E, either of those. So I mentioned both of these signs. This is proportional to the change in temperature. So please know this. This is one way to really measure the change in internal energy very fast from the change in temperature. So that's internal energy for us. Now, the other way of actually exhibiting the energy is also work. So now this whatever this change in internal energy happens, it gives out this energy in two forms. Either it will give out energy, which primarily is heat. See, in this point, we are not considering or thinking about light energy or electrical energy, all of those. Although going forward, we'll also look at that. But primarily, whatever this change in internal energy happens, this shows or exhibits itself in two forms. So what we have seen so far, we firstly saw what were systems, and we saw that systems have energy. And then we said, okay, where is this energy really lying? How is it confound inside the substance? So we said, okay, there is some sorts of multiple 7 forms of energy. All of them put together give us internal energy. Now we are talking about change in internal energy, and we are thinking about how this internal energy really exhibits. So the change in internal energy is given in two forms, either through a heat or through work. Now, whenever heat is given out, these are the sign conventions that we follow in chemistry. And I've always said this, chemistry guys are more generous. So if the system is really gaining merit, we will call that as a good system. Yeah, hi Momika. Momika has also joined in. So we say that whenever heat is given to a system, in our system we have defined system something like this. So when heat enters the system, we call it as positive heat, and when heat leaves the system, we call as negative heat. So energy transfer as a result of temperature difference. I've already said that temperature is something like electrical potential. So in for example, in electricity, as we have potential difference, and therefore electricity flows, in thermodynamics, we have temperature difference, which is very equivalent to potential difference, and therefore heat flows. Now, you'll see that we have small terms like QP and QC. We are going to look at that in just a few moments. But for the time being, just understand that, endothermic, which means heat is taken inside the system, is always positive, and heat given out of the system is always negative. So now when we talk about the work, our work is nothing but force into distance, and therefore whenever we do work on the system, we will say that the work is positive. So the bottom line of this sign convention is only two things. if the system is benefiting, and when I say benefiting, when the system's energy increases, we always call it as positive. And when the system's energy decreases, we always call it as negative. And I had given you a thing to remember because of this, that chemistry guys are always generous, which means that they only think about systems benefit, not their own benefit. In physics it is completely the opposite. In physics we think about our benefit, and therefore if work is done for us, which means if we are able to get the work output, then it is considered as positive. But here it is not as such. If it is work is done on the system, then the system's work is considered as positive, because the system is going to gain energy. And if the work is done by the system, it means the system is losing energy, the system is getting tired, had it been a living thing. So as the system loses energy, we consider that energy as minus W. Now one quick derivation from W to minus P dV is that force into distance is basically our work. If we simply divide by area and multiply by area, then force by area actually is nothing but pressure, and distance into area is nothing but change in volume. Okay, but because the change in volume in expansion is going to be positive, so if something is expanding, delta V is going to be positive, because delta V is nothing but final volume minus initial volume. So if final volume is going to be greater than initial volume, we'll find that delta plus is going to be positive. But so therefore P delta V will be positive. But according to us, if the system is doing work, which means if the system is expanding, then our work should be negative. So therefore we put a minus sign here. Okay, so W is equal to minus P delta V actually comes from the very basic thing that the work is being done by the system. One quick second. Yeah, work is done by the system. So please remember, this minus sign is something that we put in because we want to make the work negative and ascertain to the value. So there is another quick thing that I will tell you. Whenever expansion happens, work is negative, and whenever contraction happens, work is positive. Okay, contraction means positive work and expansion means negative work. Okay, yeah. Now so these are a few things about work and heat. So we had said delta U, that is the change in internal energy, actually gets converted into these two forms. Hi, Sachi has joined in. Okay, now next, so let's understand what is a state and equilibrium. Now this is one very important thing which is actually not present in the text, but to understand the concepts pretty well, this is something that we need to really understand. Now a state is something that is a position. Okay, in this thing I am talking about one instant. Okay, one instant. We are not talking about something that is moving. For example, let's say I always give this example, is that let's say you're moving from Bangalore to Mumbai. Now in Bangalore, when you started, at the moment of starting, it is an instant, that is called as a state. While you are in the travel, it is called as process or path or being in motion. But let's say you stopped at a point in Dharwad while moving to Mumbai or in Belgaum, right? So at that instant, that is another state. So what is state of a system? State of a system is that part where you will find that the system is not undergoing any change. All of its properties are known and they are not changing. And what properties are we talking about? For example, pressure, volume, temperature. We are talking about internal energy. We are talking about total energy. Okay, so all of these things are pretty constant and they are not changing. Hi Ananya, good to see you. Yeah, so all of these remain here, and since these properties do not change, that is called as the state of a system. Now even if one property changes, then the state of system has to change. Okay, now what is a thermodynamic equilibrium? It is very similar to chemical equilibrium. In chemical equilibrium, we said that the reactants and products are in equilibrium with each other, which means that their concentrations are not changing. One forms the other simultaneously, the other is also forming the first one. So this is how it was happening. But in thermodynamics, we call as the system being in equilibrium, which means that the temperature exchange is constant. If there is a heat getting from one place to the other, the heat is also coming back. Similarly, the pressure is constant. Similarly, the phases, let's say solid is changing to liquid and liquid is changing back to solid again, then both of them are in equilibrium. So all of these, whenever there is an equilibrium, again chemical equilibrium is important. So thermodynamic equilibrium is a very larger superset, you can say, of all small equilibriums. And when all of them are in equilibrium, we say that okay, there is a thermal equilibrium that is possible. Now why are these two things needed? Whenever we are going to look at an enthalpy change, or whenever we say that there are certain amount of processes that are happening, we talk from a system state to another system state. Okay, so the states change and therefore processes happen. That is the reason that states change. So therefore state is necessary, and equilibrium is a way so that we can measure things. If something everything is happening randomly, if there is no equilibrium, then it is very difficult to ascertain the properties that are there. We cannot really give values to them, and therefore thermodynamic equilibrium is also an essential important thing to really take a note of. Now let's look at paths and processes. Now that we have understood state, and taking our same example of traveling from Bangalore to Mumbai, when we are actually traveling, that's when the process is happening. And how we are traveling, are we going by a flight, are we going by a road and stopping somewhere in between, again taking another road and reaching Mumbai? That is the path. Okay, so path is the way that you are going, you're doing the travel, and process is the entire travel is the process. So when the process is happening, the process could be isobaric process, isothermal process. So what is isobaric? Pressure remains constant. Isothermal means temperature is constant. Isochoric is volume constant. Isoentropic means entropy is constant. So all of these, there are different types of processes, and all of these processes can be thought. But I just thought I will give you some examples so that you can actually remember that. We are also going to see in these processes in slight depth or slight more detail. Now in path, whenever we are traveling, let's say I'm traveling, right? So at each point of time, I know what is the velocity, what is the acceleration, what is the distance traveled. So I know all of these parameters. So all of these parameters, when we relate them to, let's say, thermodynamics, we call that as path. So it is a series of states through which the system passes while it is going through a process. So it's like while I'm traveling, how am I traveling? Which are the cities that I'm going through? Am I really stopping over at some city or not? All that is a part of the path. But just the travel, whether you are flying or whether you are going by the road, you are traveling. So that traveling is the process, and this process is defined in multiple ways. Similarly, path also is defined in multiple ways: reversible path, irreversible path, so on and so forth. So to really give some examples of different types of these processes, so let's say you have an isothermal process. Now freezing of water to ice at minus 10 degrees Celsius. Okay, now if it is freezing, now please note, I have I have not taken it as 0 degrees Celsius purposely, because I want to make sure that it can be because of different changes in pressure or temperature, you can have at any other point as well. So the moment you have freezing of water at any temperature, but once the temperature remains constant because the change in state is happening, you call that as an isothermal process. Now we also know that latent heat is given out, the very definition of latent heat, etc. was well. Okay, so all that really works. Hi Brian, good to see you here, Brian. But this is an autonomous syllabus, so if you want to look in, you can always are welcome. But just know that this is an autonomous syllabus that we are looking at. Okay, right. So now so isothermal processes is ones where temperature remains constant and the change in the substance really happens. Now in isobaric process, the pressure is going to remain constant. The pressure is something that will always be the same. So in isobaric process, one of the examples, if you have to give, it is like heating of water in open air, under atmospheric pressure. So here, because the pressure is only of the atmosphere, the pressure never changes, and therefore you will find that the change in pressure does not happen. Now similarly, you have isochoric, where volume is constant. In isochoric processes, you will realize that the volume is same, and therefore one of the examples of having the same volume is basically in a sealed metal container, you trying to do some experimentation. Okay, so heating of a gas or doing a chemical reaction. So all of that will actually help us having an isochoric process. Similarly, you can look at reversible processes. In reversible processes, the system is close to equilibrium at all times, and the changes that happen are very infinitesimally very small. They happen in a very small state, moment by moment. So that is reversible process, in which the equilibrium is between system and surrounding with the original state, and it keeps on giving in helping us have achieve equilibrium at every small points within the reaction. Okay, so these are reversible processes that are possible. And then there are cyclic processes, which are basically going from an initial state to a final state, and then again returning to an initial state. So whenever you have reactions going from one to the other and coming back, these are called as cyclic processes. So for example, whenever heat and work are done, There is one caution that we have to observe, that in cyclic processes neither the heat nor the work are zero. So both of them actually would maybe non-zero, and at the same point of time it will still help us have a cyclic process. And then the last process is adiabatic process, which is where no heat is added or removed from the system. So there is an exchange of only internal energies that are possible, as an internal energy can go up and down, but heat is not exchanged with with the surroundings. And then there can be combination of such processes. This is just an example to understand how processes really work, but it also helps us knowing what states and processes are. Yes, so hi Pranav, hi Mridul, good to see you. Yeah. Now let's go back to understanding the first law of thermodynamics. Now this is something that we have seen since very long, right? Right from seventh grade, we are seeing first law of thermodynamics is nothing but conservation of energy law. It says energy can neither be created not destroyed. At the same time, the total energy of the universe remains constant. Energy can be converted from one form to the other, but and vice versa, but there is no loss of energy at any point of time. So that's first law of thermodynamics. Now just to have a quick recap, so we understood, okay, there are substances and then there are systems which we use to understand all the energy changes that are happening. These systems further end up giving us energy. Now we also understood that this energy is stored inside the system as internal energy, and whenever there is a change in internal energy, either work is done or there is a there is a heat given out. Now when both of them are happening, they happen through a state. The states change, and as the states change, they might change through a process or through a path. So this is what we had understood so far. Now we have understood the complete background of the things. Now we are trying to understand how does this energy changes really happen. So these energy changes will happen by obeying the first law of thermodynamics, which says that energy can neither be created or not destroyed. Okay. Now to really understand this in more depth, they defined another entity which is called as enthalpy. Okay, so to have the first law of thermodynamics very well known, enthalpy was introduced. So what is enthalpy? Enthalpy is nothing but it was defined as, please note that it is a definition that we have here. So enthalpy is defined as E plus PV, where E is the internal energy at any temperature, and PV is the work function at that temperature. Please note, PV is not a like a physical quantity, but it's just a product of pressure and volume at that temperature. And this is what we called as enthalpy. Now why is there a need to define one more term? Basically, if we define this term, we will realize that whatever delta U going to either heat or work, these can be very well tackled by this definition. We'll shortly see how it really works. So once enthalpy is defined, we can actually talk about change in enthalpy, which is delta H. And what is delta H? Delta H is nothing but delta E plus delta PV. Most of the times, because pressure is constant, pressure can be taken out, and we can write this as delta E plus P delta V. Now delta H is the enthalpy, which is also called as the heat energy. So this can actually be written as QP. QP, why? Because it is the heat given at constant pressure. So whatever is the change in enthalpy is nothing but heat given at constant pressure, and therefore delta H is QP, which is another relationship that you can devise. Now, so from one to the other, as I mentioned, that delta U, which is a change in internal energy, can give heat or work. If this both of them are happening at a constant pressure, you can simply say that whatever is QP will be the change in enthalpy of that particular substance. So therefore we write it as QP is equal to delta H. Okay. Now just to understand some more of these, whenever you have a constant pressure, again recalling the definition that delta E, which is delta U, is Q plus W, as I was mentioning a few minutes ago. You'll find that we can also write delta U as QP minus P delta V, because now the pressure is constant, so work can be written as minus P delta V, and internal energy can be related with QP and work. Okay. Now so this is how we actually derive the first law in the form of delta U, Q, and W. Okay, so this is how now we have been able to relate Q, W, and delta U, or in here in our case we are writing it as delta E. Okay, so this is the heat at constant pressure. Okay. Now Now let's look at how what really is happening. So as we had mentioned, enthalpy is used to quantify a heat flow into or out of a system in the process, whichever is happening at a constant pressure. So you'll see, let's say we take a slab of water, and this water is actually formed out of hydrogen and oxygen. Now as it forms water, heat is actually given out. So this exothermic process, heat is given off by the system, and therefore the delta H is going to be negative. But at the same point of time, let's say from solid, if we are going to gaseous form, heat is actually absorbed by the system. Now we can always mention here, this is the enthalpy of H of H2O, which is in the liquid state, and this is actually enthalpy of gaseous H2 plus O2. Similarly, here we can say this is the enthalpy of H2O, which is in the solid phase, and this is enthalpy of HGO. This is HGO in the solid phase, and this is enthalpy of Hg, which is mercury, plus enthalpy of oxygen in the gaseous state. So in both of these, we understand that energy sometimes can be given in or can be taken out. Enthalpy of the system can be defined here, and system can be defined here as well. Please note that there is no difference in masses. Here also we had 4 hydrogen and 2 oxygen. Here also we have 4 hydrogen, 2 oxygen. Here we have 2 mercury and 1 oxygen. We have 2 mercury and 2 mercury, 2 oxygen. Here we have 2 mercury, 2 oxygen. So this, so you can imagine that both of them are actually having the same mass. So it could either be an isolated or a closed system. But the change in enthalpy is here simply by subtracting the enthalpy of the lower one. So let's say we call this enthalpy of the products minus enthalpy of reactants. We are able to end up getting delta H, and this delta H can then further be related to Q and W, as we had seen in the previous slide. Okay. So now in this scenario, in exothermic processes, you will find that because the heat was given out, the reactants have more heat than the products, because products were formed by giving out heat. And here you will find in the other scenario, the enthalpy of the products is more, because the products actually took in heat from the reactants to form delta H, and delta H is greater than 0. Right. So now let's look at a chemical reaction. So this is called as the enthalpy change of a reaction, where we write delta H products minus delta H is equal to H products minus H reactants. So as I was mentioning in the previous slide, from H initial to H final, as the enthalpy is decreasing, delta H is less than 0, and the heat is given out. Whereas when heat is getting in, you'll find that the enthalpy is actually increasing, and we are going from a lower enthalpy initial to a higher enthalpy final. So delta H is less than 0, then QP is less than 0. Similarly, and therefore reaction exothermic and endothermic. So this is a quick way to really look at enthalpy changes as well as being endo or exothermic. Now, how is this related? All of this enthalpy, Q, W, all of this related to our chemical equations. So the first thing that we need to understand is, what is thermochemistry? So thermochemistry is basically the study of transfer of heat in chemical reactions. So whenever there is a reaction happening, and if there is heat being transferred, then whatever studies we do with regards to the heat as well as the chemical reaction, that is what we call as thermochemistry. Exothermic, for example, in exothermic reactions, the transfer of heat is from system to surrounding. At the same time, there is a chemical reaction happening, so therefore it is a thermochemical reaction. Similarly, in end, so H2, twice of H2 plus O2 giving twice of H2O plus energy. This is actually a thermochemical reaction. Please note here in exothermic reactions, energy is actually like a product. So energy is given out like a product. Similarly, in endothermic reactions, the heat is from the surroundings to the system, and you will find that energy is like a reactant. So energy is taken by the reactants, and therefore the net energy of the products actually increase. Here is a quick diagram. So I'm trying to show you in multiple ways how enthalpy change really happens from a product to reactant, or vice versa. Now, since enthalpy cannot really be, it's basically the heat content of a substance at a constant pressure. You cannot measure the actual enthalpy directly. You can only measure the change in enthalpy. This is also one of the problems that we had basically with our internal energy, as you know of. So in internal energy, you find that the enthalpy, internal energy cannot be directly measured. Very similarly, enthalpy also cannot be directly measured, and therefore we mostly talk in terms of enthalpy change. So you can see that in the first reaction, you go from reactants to products. So the net energy goes from this point, where our cursor is, to the point that is much below. So therefore, this delta H, which is in red, is actually negative, or is because of an exothermic reaction, whereas delta H here is positive because of an endothermic reaction. So again, enthalpy of reactants is more than products. Here, enthalpy of reactants is less than products. So delta H here is negative, delta H is positive. Heat is given out and heat is absorbed. We've just seen this. Now that we have understood, okay, in exothermic, endothermic, we have seen in so detail that okay, energy and enthalpy changes, and they are either exchanged with one another. One of the most important things is to really define enthalpy, in its most standard conditions. So therefore, we use a standard condition. Why? Because enthalpy varies with conditions. With pressure, it varies. With temperature, it varies. All of that. So therefore, we fix enthalpy with certain conditions and say this is our standard enthalpy, and from here I'm going to measure everything. So for example, with pressure you measure it as 100 kilopascals, and that is basically 1 atmosphere, and the temperature is taken as 25 degrees Celsius. Please note, one common mistake that students do is take temperature as 0 degrees Celsius. No, it's basically like the room temperature, and therefore at 25 degrees Celsius you'll see that at normal all these substances which actually exist as they are in the normal lab conditions, whether they are gaseous, solid, or liquid, at that point we call it as a standard enthalpy. And from there, if we are measuring any enthalpy change, we will call that as the standard enthalpy change. So firstly, we define a standard enthalpy, which is at 1 atmosphere and 25 degrees Celsius, or even at these pressure temperatures, we will measure all the other changes that are happening, and those changes are called as standard enthalpy changes. So it's sometimes also written as with a not sign, like a simple circle, or a circle with a bar in it, called as delta H naught. So that's the symbol for standard conditions. So now let's look at some enthalpy changes that we have. Okay, so one of the most important enthalpy changes is enthalpy of formation. Now, enthalpy of formation basically means is that how is the substance is forming from its root causes. Okay, this is most of the times, but not always. This most of the times exothermic. In a very few circumstances, it is endothermic. For example, you will find a melting of ice. So water formed from ice, is an endothermic process. Okay, but it's not typically a delta H formation, but I'm telling you a process that is endothermic yet very natural and spontaneous. So most of the times, enthalpy of formation is actually exothermic process. Please note, we need to form 1 mole of the substance. Okay, it's not 1 mole of reactants, it's not 1 mole of intermediates. It is 1 mole of the product that is formed. So in all the cases, we'll find that it is 1 mole of product that is getting formed. We are taking this as a fraction, that is okay, but I need this as 1 mole. Okay, so whenever we make 1 mole of a substance form, we call that as enthalpy of formation. And so you see, I've written a note here that it is always 1 mole on the RHS of the equation. RHS is the right hand side of the equation. So here we have to have 1 mole. Whatever fraction you want to put on the left hand side, you can do that. Now, one more very important thing here is enthalpy of formation, is that if you use any elements, their enthalpy of formation is always 0. For example, here O2, C, H2, O2, carbon, all of these are, their enthalpy of formations are always 0, elemental forms, because elemental forms means that they are in the same form naturally occurring, right? So therefore their enthalpies are 0. Now, carbon is not taken in any other form except for graphite. For example, carbon can also occur in coal, or can occur in diamond form, but those are not taken. So enthalpy of formation is the way that 1 mole of a substance is formed from its elements, and these elements should also be in their standard states, and that's when we call it as enthalpy of formation. Now, similarly, we have enthalpy of combustion. So enthalpy of combustion is when 1 mole of a substance is consumed. Please note, there on the other side we had 1 mole on the RHS. Here we'll have 1 mole on the LHS. So 1 mole of what you are burning. Okay, so whatever you are burning, that should be 1 mole. For example, here graphite is being burnt. Here hydrogen is being burnt. Here C2H5 is being burnt. All of them you will see we have taken only 1 mole. Oxygen can be anything. The product that can be formed can be anything, but something that you're burning always has to be 1 mole. Okay, so that's basically 1 mole of enthalpy of change for combustion. Yeah, hi Mansi. Okay, no problem. But so guys who have joined in late, if you have missed out something, you can always go back, look at variable speeds, connect to the topic that you have really not understood, and revise things. You can always message me if you have any doubts, guys. You can message me on the chat window here, or on WhatsApp. In either of those, I will be able to answer you. Okay, so that's a quick look at the enthalpy of combustion. Now, please note, enthalpy of combustion is when it is going to a certain complete combustion. Okay, you will find that there is one more enthalpy of combustion where you have carbon plus oxygen actually giving CO. Okay, half O2 giving CO. Now, this is not complete combustion. Okay, so this can be the enthalpy of formation of CO, but this cannot be the enthalpy of combustion of carbon. Okay, very important point, because here you'll find that carbon has not gone complete combustion. It has not gone to its maximum state of combustion or naturally occurring compound of oxygen. Unless the CO2 is formed, combustion is not typical. Okay, so that's a very important point of this. Okay, now let's look at okay, so this is when we have seen enthalpy of combustion. Now the next is enthalpy of neutralization. So these are different enthalpies that are possible. So we have seen formation, combustion, and then this is the enthalpy of neutralization. Now in enthalpy of neutralization, basically one H plus and one OH minus forms one H2O. Please note, the basic definition is when 1 mole of water is formed. So water has to be 1 mole, whether you are taking it from, how you really are making it form, whether it is formed from H plus or OH minus, or you take HCl and NaOH, or you take half of H2SO4 and maybe half of CaOH twice. All that is irrelevant. At the end of the reaction, you have to have H2O plus, whether if there is a salt formed, that is okay. Salt formed is okay, but 1 mole of H2O is very important. If 1 mole of H2O is formed, that is what we call as enthalpy of neutralization. Now, please note that enthalpy of neutralization of any strong acid, strong base, which means at any point of time only H plus and OH minus is reacting, it is always minus 57. In fact, minus 57.1 kilojoules per mole. Please note, it is kilojoules per mole. I see a lot of errors where people write it as joules per mole. They sometimes forget the sign. Minus sign is forgotten. See, minus sign because this is an exothermic process. Please note, enthalpy of neutralization is always an exothermic process. So therefore, whenever enthalpy of neutralization is dealt with, you should always consider a minus sign. Now, one more very important aspect of this is that we have mentioned strong acids and strong alkalis because we imagine that strong acids all entirely give out H plus and strong alkalis entirely give out OH minus. What happens when there is a weak acid? For example, you have CH3COOH. Then you'll find that 1 mole of CH3COOH is never going to give entirely H plus. Maybe you will only end up getting 0.02 moles of H plus. So therefore, there is some energy lost in dissociating also. And hence, this minus 57 comes down to probably, let's say, minus 51. Sometimes it is minus 49 also. Why is this 6 joules of energy, which was supposed to come to us, is now not coming, not reaching us? Is because the molecule itself is utilizing this energy to dissociate itself. So CH3COH is dissociating into H plus, and that's how the reaction, the neutralization is happening. So that's enthalpy of neutralization. Again, just to quickly have a look, enthalpy of neutralization is when 1 mole of water is formed. So I have taken 1 mole of water again. Okay, so that's a quick look at enthalpy of neutralization. Now there's another very interesting and very important enthalpy, which is called as the bond dissociation enthalpy. So you'll see, whenever energy is required to break 1 mole of gaseous bonds to form gaseous atoms, 1 mole of bonds. Please note, this is not 1 mole of atom, 1 mole of molecule, 1 mole of any substance. No, 1 mole of bonds. Now see, in Cl2, 1 mole of Cl2 will have 1 mole of bonds, but 2 moles of atoms is formed, which is okay. In OH minus, there is 1 mole of OH will give 1 mole of oxygen and 1 mole of hydrogen. Now let me give you another example. Let's say I have CH4, then 1 mole of CH4 will give me 4 moles of CH bonds. Why? Because each Cl is connected to 4 hydrogens, and therefore there are 4 moles of CH bonds. So I will have to ideally take 1/4 of CH4 dissociation into CH to actually get the bond dissociation energy. Okay. Now, bond dissociation energy is most of the times, in fact, all the times you'll find that it is actually an endothermic process because you'll need energy to break the bond. So you'll have to give energy to break a bond. So bond dissociation enthalpies are always positive. Okay, they are always positive energies or positive delta H. Okay. Now making bonds is exothermic because it is opposite of breaking a bond. So when you are breaking a bond, it is always endothermic. For diatomic gases, bond enthalpy is 2 into enthalpy of atomization. Okay, now this is a very important thing. Now please note, what is enthalpy of atomization? Enthalpy of atomization is to form 1 mole of atom
chlorine. Okay, so if I were to form 1 mole of chlorine, I'll have to take half of Cl2, isn't it? So if I'm taking half of Cl2, you'll realize that we are basically talking about half of bond enthalpy Cl. So therefore, I've mentioned here that for a diatomic gas, bond enthalpy is equal to twice into enthalpy of atomization. Okay, which means that whatever atoms are getting formed. What is enthalpy of atomization? Enthalpy of atomization means energy required to form 1 mole of atom. So there are multiple of these enthalpies that you can define, but in all of these cases, most of the times it is only 1 mole that you are looking at. What exactly is 1 mole of bond? Okay, so Pranav is saying what exactly is 1 mole of bond. See, Pranav, 1 mole of bond means you need to have bonds which are equal to 1 mole in quantity. Okay, what does that mean? So for example, let's say I have CH4. Okay, now if I take 1 mole of CH4, then I'm going to take basically 6.022 into 10 to the power 23 molecules of CH4. Now, in each of these molecules, I have 1, 2, 3, and 4 bonds of CH each. So, if I have so many CH4 molecules, I basically have so many divided by 4 CH bonds. Into 4 CH bonds. The other way around. I basically have so many molecules into 4 because each molecule has 4 into 4 CH bonds. But for us, we only have to define or deal with 1 mole of bond, which means only this many number of bonds. So whatever is the formation energy of CH4, that divided by 4 will be giving me the bond enthalpy or bond dissociation enthalpy of CH. Are you getting this? Yeah. So 1 mole of bonds means basically 1 mole in number. 1 mole, like I have 1 mole of carbon, 1 mole of oxygen, 1 mole of hydrogen atom. So this is 1 mole of oxygen atom, 1 mole of hydrogen atom. Similarly, in this thing, I have Cl. So I will have 1 mole of bonds inside them. Okay. Yeah. So that's 1 mole of bond enthalpy. Now, of course, now smaller the bond enthalpy, weaker will be the bond and easier to break. If the bond enthalpies are very large, implies they are very strong bonds, and they will be much harder to break. Okay. Now, okay. So that's bond dissociation enthalpy. Okay. Sorry. Now let's go to the next. We'll look at a few bond enthalpies. Now please note, single bond enthalpy and double bond enthalpy doesn't mean that double bond is twice of single. Okay, this is a common mistake that people do. So double bond might be very different. Triple bond is a different kind of a bond. So triple bond enthalpy is not that equal to single bond. I have shown you here. For example, 346 is a single CC bond enthalpy. But if you look at the triple bond enthalpy, it is 837. It is not 3 into 346, which will be somewhere around 1000 kilojoules. It is only 837 kilojoules. Okay. So the actual value is something that is experimental. And for each of them, you will end up getting some bond enthalpy. Okay. So I've given you all the bond enthalpies for different atoms. For example, HCI, just for you to really have an idea. Now, 1 mole of gaseous bonds to form gaseous atoms, right? And they are always endothermic. We have seen this. Okay. Now, most of the times it is the mean value that you will take if there are multiple bonds that are present. Okay, for diatomic substances, we have also said, bond atomization and smaller bond enthalpies. Okay, so this we have really seen once again. Okay, now, sorry. Now let's go to the next. The next is, now that we have understood bond enthalpies and we have understood first law of thermodynamics, a quick recap for everyone who has joined late, because this also keeps us having the flow. Firstly, we understood what was the system, and we said in this system, once again, in this system, we said that there is energy, and this energy is getting exchanged with others. So we said, what is that energy? Where is it residing? So we said, okay, boss, there is something called as an internal energy, which comprises of 7 factors. Okay, we said that's fine. So what happens when internal energy changes? We said it either gives as heat or it gives as work. We said, okay, but how do we measure that? So we brought in a term called as enthalpy. And then the enthalpy was there. We said delta H is something that is change in enthalpy. We said, why are we talking about delta H? We said because we can only talk from state to state. We don't need to talk about all the processes that are happening in between. So if you are talking from state to state, we can directly talk about internal energies and get the work done with. So we said, okay, that looks great. So therefore, delta H is nothing but QP is what we derive. Okay, it is the change in heat at a constant pressure. So after we have understood all of this, then we said there are multiple types of delta H. So we saw delta H combustion, we saw delta H formation, we saw delta H, which is bond dissociation. Then we saw delta H atomization, delta H neutralization. We also saw delta H. There is another delta H which is called as fusion or delta H vaporization. So all this is basically for different enthalpies that can change from one spot to the other. So all that is okay, but now sometimes all of these enthalpies we cannot really measure. Okay, so when we are not able to measure enthalpies, how do we really understand what is happening? So what we do is we use indirect methods to measure these enthalpies. For example, there is, Hess gave a very interesting law, which is a very important law, and he said whatever enthalpy change you are doing, it is independent of the path. Okay, don't worry about the path. You simply go and do the enthalpy change. At the end of the day, the enthalpy changes will be the same. So he said, okay, look, one, you are going through flight, and let's say you are going through road. At the end of the day, you will be reaching Mumbai from Bangalore only. Okay. So if you are reaching Mumbai from Bangalore, just by looking at these two, I will be able to tell you at least some information. For example, I will be able to tell you what is the net distance you traveled. I will be able to tell you what was the net time you took. Okay. I will be able to tell you where is your geographical location. Okay. So maybe not all. This is a very important point. Maybe not all, but some entities I will definitely be able to tell you. This is what Hess said. Okay. So he said, okay, definitely one of the things that I can surely say is about enthalpy. So he said, okay, interesting, looks interesting. Let's understand how. So he said, when enthalpy changes, going from A to B, the values of enthalpy changes from, let's say, from one route it is from A to X, X to Y, and Y to B. And let's say at each of these it is delta H1, delta H2, delta H3. Then the summation of this second path and summation of the first path will be the same. Tomorrow, if you go through some other processes, let's say 1, 2, 3, 4, 5, and then 6, all of them put together also will end up giving you the same enthalpy through as through this process H. Now, please note, when we are directly talking about A and B, we are basically talking about then enthalpy of reaction, because we just a few minutes ago we discussed enthalpy of reaction is nothing but enthalpy of products minus enthalpy of reactants. So when we are simply talking about enthalpy of reactions, you will find that delta H1, delta H2, delta H3 could be any other enthalpies, but their product will come out to be the same. Okay. Now here is a few, what happens if you go in the opposite direction? Okay. Now if you go in the opposite direction of the arrow, instead of adding the value, you will subtract the value. Okay. So let's say, for example, from X to A, I went in the opposite direction from, so delta H2 is this. So in X and Y, this is delta H2. And if I have to go from X to Y, I'm going to go in opposite direction here. Then I'm going to go in the same direction, and then I'm again going to get into the opposite direction. Because I went in the opposite direction at delta H1, I have written a minus delta H1. Now delta H2 is what is through one path. This was on my path 1. Okay. And this was entirely my path 2. So path 1 delta H2 is equal to minus of delta H1 because I went opposite. I am going in the same direction, so I'm keeping delta H3 HR as the plus. And here also I'm going in the opposite direction, so therefore I will make it as minus. So minus plus minus, that is how you can actually end up getting the same, delta H in both the directions. So if you change the direction of the reaction, you will realize that your delta H will become negative. There is one more interesting thing here. What happens if you trace the same path twice? Okay, so let's say this was my path 1 and my path 2 is this, then I come back again, then I go back again and I come here and then go here. Okay, maybe some path like this. So what I will do is, because I did this twice, because I went twice upstairs, I will write this as minus 2 into delta H1. Okay, please note this. I will return it twice. Why? Because I went twice up. Okay, and I came one down. So I am going to take this as plus delta H1. Okay, only at these 3 steps. Then the other things will remain same. Plus delta HR, minus delta H3 will remain same. But the important point is, so if you trace one part twice, you will have to add it as many times and remember the direction. If it is still twice in the opposite direction, you will write 2 negative, and once in the straight direction, you will write 1 positive. Okay, so that's one interesting thing. Now, a few more applications of Hess's law. So how do we really use Hess's law, right? So Hess's law enables one to calculate those enthalpy changes, which we cannot directly actually calculate. Okay, so I've given some examples here. So let's say changes which cannot be measured directly, like lattice enthalpy or enthalpy change of a reaction from bond enthalpy. So we know bond enthalpy, but we don't know change of a reaction, which is delta HR. But I know what are the bonds. For example, CH4, I know the bond energies, but I don't know what happened in the reaction and suddenly CO2 and H2O was formed. So if I have to find this energy, then I know the energies of CO2, I know the energies of H2, and I know energies of this guy. So I will take this as, let's say A, I take this as B. So A minus B will be my enthalpy of reaction. So enthalpy of reactions from bond enthalpies can be formed. Similarly, enthalpy of reactions from formation enthalpy or combustion enthalpies can be formed. So using different other enthalpies, those enthalpies that is missing with you can be traced. Okay. So these are a few ways to really write Hess's law. Now, just to really do one example, how we can really do it from bond enthalpies. So basically, let's say imagine we have during a reaction, the bonds are being broken from individual atoms and they are forming new bonds. That is what basically happens in a chemical reaction, isn't it? So let's say these are reactants and these are products. Now the energy of the reactants was more than the energy of the products, which means that the reaction was basically an exothermic. Okay, the energy of reactants. Then it also means that I basically broke all of these bonds. So therefore I needed bond dissociation enthalpy here. Okay, and then I formed gaseous atoms. And from here I formed products. So I had a reverse of bond dissociation, which is basically bond enthalpy. Okay, so here the energy is given out and therefore there will be a minus delta H here, and here there will be a plus delta H. Okay, so from reactants to products, as we go, we will realize that the bond enthalpies of reactants can be utilized so as to imagine that the bonds were being broken, and as the bonds are getting formed, the bond enthalpies can then be added one more time. So energy is put to break bonds to form separate gaseous atoms, and then energy is again taken out as the bonds are formed. So energy is released. So by using Hess's law, basically, and adding step 1 and step 2, you can find the delta HR between reactants and products. So we are trying to find the energy of the reaction going from reactants to products through bond enthalpy additions and bond enthalpy, bond breakages and bond additions. Okay. Now, so that's bond enthalpies. Now let's look at an another way. The way that we can actually understand this is, see, when we actually broke the bonds, we had to give in energy. So let's say if reactants were here, this was the energy to make them into atoms. So I gave energy, so the energy of the entire system has risen by so much. Okay. Now from here, as the bonds are formed, new bonds are formed, the energy simply drops. Okay. So all the energy that has dropped from this point to the points of products, you will find that the energy is given out. And as the energy is given out, you will realize that the energy of the entire system has gone down, and therefore net the delta H is negative, which means that the reactants have a larger energy than the products. Reactants have, yes, a larger energy than the products. Okay. So this is another way of looking through an energy diagram. Another way to really look at it. Gaseous atoms combine and therefore they give out energy. Now, because I'm going in the opposite direction, I'm using a minus sign in step 2. Okay. I hope all of you guys are getting this and you're connecting. Please keep on responding if there is something that you really do not connect. Maybe I can go over it one more time. I hope that this is something that you guys are really understanding. Okay, we have done many equations on this, but I just wanted to have a quick look at all of these individual problems, and therefore I wanted to mention this. Okay. Okay, good. Yeah. So okay. Now let's look at the next way to really look at that. Another way to look at that. So basically, I had a molecule, and I'm breaking up all the bonds of this molecule. So I got only the atoms. There are no bonds here. So delta H2 was the energy given out. And let's say when new compound is formed out of it, you will find that delta H3 is energy that is basically required. So as you go back, you'll realize that delta H3 is produced from delta H2. So the delta H1 in this scenario will be nothing but delta H2 minus delta H3. So negative is used because I'm going in the opposite direction. Okay. So that's enthalpy of reaction from different bond enthalpy. Okay. So here's an example. Let's say I had delta H2 given to us. These are different bond enthalpies given to us. Then all the CC double bond energy was 611. CH bond energy was 413. HS bond energy is 436. So you'll realize that the total energy to break the bonds was 2699. So delta H2, so much of energy was given out. And while the new product was formed, we'll realize that so much of energy we had basically one CC bond but six CH bonds that were formed. So you end up getting 2824 energy is released. So 2699 minus 2824, in total you end up getting 125 kilojoules as the net energy that is given out. So here's a quick example, the way to that you can actually write the reaction. In exam also, if you're able to write it in this form, instead of just at, you can write that, 80, and you can also say 611 kilojoule. If you really write it in a systematic form, one below the other, I don't think so that there will be a problem in, solving any of these questions or you getting anything wrong. Okay. Good. So, before I go forward, it would be nice if you guys can just put in a yes, no, if you're connecting, if everything is okay. I understand that a few of you are still there, a few might have dropped out. Okay, I'll just look into that, but just let me know just in case if you're connecting and all is okay at your end. Okay, so moving forward, enthalpy of reactions from enthalpies of formation. Okay, now enthalpies of formation are from elements going to reactants and products. Okay, okay, good. So basically, when elements go from when we go from elements to reactants or elements to products, you'll realize that delta H formations is what we are really looking at. So, so basically, what happens is, uh, 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 look at the arrows that I've mentioned. Okay, minus and plus. So when you're going from reactants to products through this way, you will realize that I will have to use minus delta HF of reactants. Maybe I'm going to change the color. Okay, this might not be visible. Yeah, so I will have to do a minus delta HF of the reactants to elements. And after that, I will have to do a delta plus HF from elements to products. So this will be a positive one because I'm going in the direction. And this will be a negative one because I'm going in the opposite direction when I move from here to here. So this is another way where you can use the enthalpy of formation basically to go from reactants to products uh, through either a delta H reaction or in the opposite direction. Okay. So this is another way where you can relate delta H formations with the enthalpy of reaction, and you can actually solve a few problems on those. Okay, so I've basically mentioned multiple examples. Just to quickly recap, we have seen enthalpy of reaction from bond enthalpies. We have seen enthalpy of reaction from combustion reaction. We have seen enthalpy of reaction from formation reaction. So all of this is also pretty important. So you'll realize that from elements you're going to reactants first, and from reactants you're again going to products. So all the time, since you're going in the direction of reactants and products, you will simply keep on adding the energies if you go in this fashion. So here this will be negative, but this will be positive. So ways to really write down different ways to really write down the energy equations and put the right signs. Okay, so delta R of this reaction is nothing but delta H formation of products minus delta H formation of reactants, both of them. Now please note that I have used a minus sign here because from reactants to go to elements, you will have to give in energy. So that is in a different way or in the opposite direction with that of actually formation of the reactants. Okay, now here's an example, a simple calculation that I wanted to show you. So let's say you have enthalpy change. They've asked you to find the standard enthalpy change for the given reaction. Then the standard enthalpies of formation are for water, for nitrogen, for oxygen, and for HNO3 they are given. Obviously, for oxygen it is going to be 0 because it is in the elemental form. And you have to find the enthalpy change of the reaction as such. So what you'll do is you'll basically take up the enthalpy of formation of products. Now please note that there are 4 moles of HNO3 that is getting formed. Okay, so I will have to multiply 4 into delta HF of HNO3 minus, because now the reactants are not getting formed. In fact, you are breaking down the reactants into elements. So I'll have to use a negative sign because I'm going to go into the opposite direction. So you will multiply twice into that of delta HF of H2O because I have twice of H2O that is getting broken down and 4 of NO2 that is getting broken down. Okay, so 4 into delta HF of NO2. And then 1 of O2, this is basically 0, so I don't need to really bother about it. Now, please note when I'm substituting the values of delta HF, I'm substituting it with the sign. Please note for NO2, it is positive, that is what they are given it to us. And for H2O, it is negative, so I've substituted delta HF values as it is. In HNO3 also, it is negative, so I've substituted as it is. And once you solve this equation, you'll end up getting the final answer, which is nothing but minus 252 kilojoules. Now, what I'm going to do is, what I would suggest, just after the class, in all of these questions, I've done two problems already. One with the bond enthalpy, second with enthalpies of formation. I really want you guys to, pause this video, after the class, because we might not get enough time right now. But if you can pause this video after the class and really look at, how these problems were done, just look at the question, try to, solve it yourself, and then come back to really understand, what did we do and how did we solve. Okay, so that really would work. Okay, now let's okay, now let's look at the next one. uh, Now, this is with combustion. Okay, so we have not done the entire equation with combustion as such. So we are the another example that I wanted you to look at. So you will see that enthalpy of reaction is basically from reactants to products. Now you'll see whenever we do a combustion, mostly CO2 and H2O is formed for organic substances. Okay, so when reactants go to their oxidation products, when products also go to their oxidation products, in both of these, enthalpy of combustion is happening. Now, in delta HR, we'll go from reactants to products. So here I'm going from this direction, so this will be positive, but this will be negative. So you will realize that I can write delta H equal to delta HC of reactants, which is positive, minus delta HC of products, which is actually negative. Okay, so minus sign comes on the product side, and therefore you will be able to realize that delta H combustions can also be taken out. So just to show you here, delta H combustion can also be written as delta HC of reactants minus delta HC of products. Okay, so they both can be really looked at, and we can understand the delta H reaction from combustion reaction enthalpies. Say again the same way, delta, we are going to the oxidation products. Oxidation products are, see, in all of these, there is one trick. Oxidation products, I have always taken it as the lowest enthalpy, but if you really look at elements, I have taken at the highest enthalpies. So automatically all my directions get fixed whenever I take their natural enthalpies. Okay, so here the enthalpies are very high, and here the enthalpies are very low. Okay, so when I go from products to oxidation or reactants to oxidation products, the enthalpies will be automatically seen, right? Now, when I'm going from products to reactants, I will have to go in this direction. So products to reactants, I'm here. I have to go all the way through this, right? So when I go from products to oxidation, you will see that the combustion comes out to be. Now look at the direction, the red direction that we have taken. Okay, I'm going from reactants to the products, and I'm going from this direction. So the green one is positive, and the blue one is negative. Blue one is the combustion of oxidation and products, so therefore minus of delta HC products is mentioned. Okay, so this is one. Now here's another question that I just wanted to show you. So let's see that the standard enthalpy of formation of methane is taken, and standard enthalpies of combustion of carbon and hydrogen and methane is here. So you can realize that graphite is what we will use as the elemental form of carbon. So whenever we are using graphite, the formation is of ammonia from carbon as well as hydrogen. Now, if we use the enthalpies of combustion, graphite will go to CO2 and H2O will go to H2O. So if the combustion is happening of graphite, they have given the combustion enthalpies as minus 394 and minus 286 and minus 390 of CH4. Using our previous equation, which is delta H C of reactants minus delta H C of products, you'll see that reactants enthalpies can be written 2 into. Now, please note again, we have written 2 here because there are 2 moles of H2 that are getting combusted, okay, or that are getting burnt. So 2 into minus 286, 1 into minus 394, and since there is only 1 mole of CH4, again minus of minus 1 into minus 1, 890. Then you will end up getting your final answer. So again, this is reactant minus products. So please note, I'm time and again I'm saying, this is one of the simplest way that you can really represent. Okay, so I'm telling you not only in one way but 3 different ways. One way I'm showing you by these arrows. Remember these arrows that reactants, products, and oxidation products can form. Remember these arrows where you can have states of enthalpies from lower, higher, increase, decrease. And the third way is you can simply write it through the formula. If you can remember the formula, any of these 3 states, if you are able to remember, you will end up getting the right answer. Okay, now Just a quick summary. So what we have seen so far is that the change in enthalpy that occurs when reactants are converted to products is the same whether the reaction occurs in one step or multiple steps. That's what is Hess's law. The second thing that we understood in Hess's law was it can be used for calculating all of those enthalpies which we cannot directly really calculate or directly connect to. Okay, so that's another way. Now, when we are doing a stepwise reaction to determine an overall reaction, we can actually manipulate the equations depending on our convenience. For example, if we are given combustion, then we'll take only combustion. If we are given formation, we'll take formation, so on and so forth. So by manipulating all of these equations, you will end up getting the final enthalpy. Okay, so that's what we do. The next is at each of these steps, whenever we are manipulating, we write the right delta H. So I told you that delta H not only depends on temperature and conditions, but it also depends on the number of particles. It also depends on the type of particles, solid, gaseous, and all of that. So all that put together, you will realize that the delta H values for each step is rightly written, and from there overall enthalpies are calculated, okay, of the desired reaction. Now let's look at one more example where we are trying to use Hess's law and solve. But this is a more general example. So far, we are only seen through combustion or formation energies. This is a general example. So here we are taking H3BO3, which is nothing but boric acid. It's actually getting dissociated into HBO2 plus H2O. And H2B4O7 is also with water is actually giving 4HBO2. There are three reactions that have been given to us, and their delta H reactions have been given. Okay, so reactions and their enthalpy change of reactions are given to us, and we need to find the delta H for a new reaction which is not a part of any of the earlier reactions. Okay, now please note this reaction is not present in the above part. So what do we do? So now we write all these reactions that are there with us. We try and get these reaction through a simultaneous reaction process. So this is what I can do. So I need twice of H3BO3. So I will multiply this by 2, the first reaction by 2. The moment I multiply by 2, I get 2 to 2 every pair, everywhere. Okay. Now the next is I need B2O3. Okay. Now B2O3 is here. Okay. But it is twice of B2O3. So therefore I will divide by half. Okay. I will divide by half or multiply by half. So this I found out that delta H for this reaction, which is nothing but twice into this thing, which is minus delta H4. Now here, because I need only B2O3, I'm dividing by half. Okay, so in this process you will see that I need HBO2. So I'm dividing it by 2, and here also I'm multiplying by dividing by 2, so I get B2O3 and half H2O. Now all of these put together, I found all of these. Now once I add them, look how it cancels out. So twice HBO2 cancels with twice HBO2. H2B4O7 cancels with H2B4O7. And once you add all of them, you end up getting your desired equation, which is nothing but twice H3BO3 plus B2O3. Now, please note in the second reaction, because we wanted, twice of HBO2 cancelled out, therefore we multiplied by half. Okay, because we had a reaction with four, uh, the HBO2 reaction is here. Yeah, we had 4 HBO2 reaction. Also, this reaction was actually reversed. I only need twice of HBO2 because here I had multiplied in the first reaction, I had multiplied by 2. So I'm reversing the reaction, therefore it is not no more minus 11.3, but it is plus 11.3. At the same time, I'm also dividing it by 2 because I need twice HBO2 to be cancelled out. This twice HBO2 has to be cancelled out. So reverse the reaction and then divide by 2. Because I reversed, 11.3 becomes positive 11.3. Please note it has become positive 11.3, and it has also got divided by 2 because I divided the reaction by 2. The entire energy was divided by 2. Similarly, here also we divided it by 2 because I did not need to reverse or anything. And then simply add all of those. All of these will cancel out and you end up getting your final reaction. So you simply add the energies now. So minus 0.04 plus 5.65 plus 8.75. You will end up getting a final answer of 14.36. So this is one way to really, solve this question. Okay. Now, so this brings us to the, end of this chapter. I'm just uh, Pranav, we've already done equilibrium, chemical equilibrium. We have already done in the very first, chapter. If you want, just ping me on WhatsApp and I'll send you the video YouTube link for that. So, just buzz me after this session and I can send you the video link. By the way, guys, the equilibrium class, the volume was pretty bad. So I had actually modified the volume and made a new video out of it, which I had also posted on the group. If you feel that you still want
that to be, you still want that video one more time, just ping me on WhatsApp and I'll share the video link with you. Okay. Good. So I just want to pause here for a minute, and if there are any questions, if you feel that you want to know anything more about equilibrium, because that's the end of the chapter. We have seen all different types of enthalpies, reactions. We have seen how thermochemical equations really differ or they matter. So if there is anything that you would like me to really speak about, please feel free to ask now. And then I'll quickly revise the entire chapter, and then we can wind off. But I'm happy to hear out your questions before we really do that. So I'm just pausing for a few seconds, and I'll wait for you to really respond on any questions that you may have. Okay, so I think most of you, it seems. Okay, so let's quickly look at what we've understood today. So we have understood what were exothermic and endothermic reactions. We have also understood the reasons for standard enthalpy changes. Please recall all the definitions. You can actually say a yes or no on this. If you have really understood this chapter well and this presentation well, you should be able to do all of these things that I've written here, and you can mention whether it's a yes or a no based on these two. Okay. Now, we have understood what are the reasons for different changes in enthalpies and what does enthalpy really depend upon. How is it connected to the first law of thermodynamics, as well as the change in heat and the change in work. We have also understood how to write equations of enthalpy of combustion, enthalpy of formation. How to recall and apply Hess's law. How to also recall the definition of bond dissociation enthalpy. How to really write bond dissociation enthalpy. We've also seen standard enthalpy changes using bond enthalpy values, and standard enthalpy changes of formation and combustion. Okay, so that's a quick aspect of all the enthalpy changes and energy changes in in chemical reaction. Good. So nice. I can still see that a few of you are there. Some of you have already left. If there's anything, I'm available. You can always buzz me. Else, we can call it a, we can close on the session for now. Please let me know. Thank you so much. If I'm here for the next few minutes. If you feel that there's something that you would like to really speak about, we can do that, or else we'll close up on this. Okay, so thank you so much, guys. I wish you all the best. Write the answers well, and I'll see you soon on the next session. Thank you. Bye. Thanks, Kirtana. Thanks, Aditi. Thanks, Pranav. Thank you so much, guys.